Okay, so MSL13 was giving some folks some trouble. So uh, questions number 6 and 7 in particular included some questions about um, confidence intervals, which I didn't really go over for the slope coefficient. So I've removed 6 and 7. They might still show up for some reason, but I've removed questions 6 and 7, so you don't really have to do them for this assignment. What I am going to do, though, is I'm going to talk about how to do number 5. I think that if I run through number 5, number 4, which has kind of a subset of the questions on it, should be a little bit more straightforward. Okay. Now, these questions ask you to kind of use the regression ANOVA table without actually it being given. But I'm going to show you, and I'll post this on D2L. This is really what the regression ANOVA table looks like. It's very similar to the other ANOVA tables that we had, but there's a couple of useful facts in here that will come up and will be useful for answering that question. So just to note here, remember that we're looking for the sources of variation, in this case the variation in the dependent variable, and there is the source of variation that we've explained, which is here in the regression, and then there's the variation that we have not explained, which is in this error row right here. So we have the sum of squares, and I showed how to calculate these before, but this sum of squares, SSR, is the sum of squares regression, and then this is the sum of squared error, and this is the sum of squared total. And what goes in this column is the degrees of freedom. Now notice that the degrees of freedom for for SSR is k, which is the number of independent variables. And the degrees of freedom for the SSE, sum of squared errors, is n minus k minus 1, where n is the total number of observations. And the degrees of freedom total is just n minus 1. Okay, so I'm going to make reference to that as I work through this problem number 5. Okay, all right, so this tells us that a multiple linear regression model based on a sample of 32 homes is developed to predict the appraised property value based on land area of the property and age in years. Okay, so we're predicting the appraised value on the basis of two independent variables, that is the land area and the age. Okay, so they give us the SSR and they give us the SSE, and much of what we're doing here is just working through some of this regression ANOVA table. Okay, so so part A says determine whether there is a significant relationship between appraised value and the two independent variables, land area and age, at the 0.05 level of significance. Okay, so that's kind of like the whole question, but we just need to go through it piece by piece. So we'll just, we always start off with the hypotheses. Okay, so what are the correct hypotheses to test? Okay, now with a multiple regression, the null hypothesis is that all of the variables don't have any impact on the dependent variable at all. Okay, now in this case we have only two independent variables, land area and age. So the null hypothesis is that the beta, this is the coefficient for the first variable, and the coefficient for the second variable is 0. Okay, so that's going to be our null hypothesis. There's only two variables, and the null is that the coefficient for both of them is 0. And so the opposite of that is that at least one of them is not 0. So in this case, again, there's just 1 and 2, and we're saying that at least one of those is not 0. Okay, all right, so we'll check that. Okay, so now we have to calculate the F statistic. Okay, so over here, we see that the F statistic is the ratio of the MSR and the MSE. Now, we're not given either of those, so we're going to have to kind of construct this table here to get to those. Now, remember that in order to get to the mean squared regression, we just have to divide the sum square regression by the degrees of freedom. Okay, so let's go ahead and see if we can figure out what all those are. So I'm going to put, we'll kind of make a mini Anova table here, and this will be error. Okay, so the over here we're going to have the sum of squares. So the regression sum of squares, or this is called the let me think of a nicer way to organize this. Okay, so the sum of squares regression and sum of squares error. Okay, I think this will be easier to understand. Okay, so we're given that the SSR is 33,015. Okay, and we're given that the sum of squared error is 100,530. Okay, so now we've got these, and we just need to find out what the degrees of freedom are. Okay, so if we consult this table again, the degrees of freedom is just k, that is the number of independent variables, which in this case is just 2, right? Land area and age. And so if we look down here, we see that the degrees of freedom for this part is n minus k minus 1. Now, how do we know n? Well, n was given to us in the problem. Let's see if I can find that window again. Okay, so it tells us that we have a sample of 32 homes. Okay, so n is 32. So we have 32 minus the 2 independent variables, so that's 30, minus 1 is 29. Okay, so our degrees of freedom here is 29. Okay, so what's going to go here is going to be our MSR, and this is going to be our MSE. So mean is just the sum divided by the degrees of freedom. So we'll just set this equal to this divided by this. Okay, and so this one is going to be equal to this divided by this. Okay, so now how do we get our F statistic? If we go back to that table, we'll see that the F statistic is just MSR divided by MSE. Okay, so I'll put that here. So the F is going to be equal to MSR divided by MSE. Okay, all right, so that's the actual F statistic. Let's see, so it wants 2 decimal places, so it looks like 4.76. Okay, 4.76. That's a fairly large F. Okay. Now, so now we have to find the p-value of that particular F statistic. Okay, and to get okay, so we're dealing with an F distribution here, so we need to do F dot dist. Okay, but remember that this is going to give us the area to the left underneath that F distribution curve. So if we want to find the p-value, remember that that's going to be the probability that it's out there to the right. So we want 1 minus this. So it's going to be 1 minus F dist. Okay, now we just need to put that F statistic in there. And we have 2 degrees of freedom. Now, so this is going to be the numerator degrees of freedom and then the denominator degrees of freedom. So we've got 2 for the numerator degrees of freedom, 29 for the denominator degrees of freedom. Okay, and we always put true. Okay, and I've got the paren backwards there. Okay, so this wants 4 decimal places, so 0.0163. 0.0163. Hopefully this is right. Okay. Okay, so now we have to state the conclusion. So notice that the p-value is fairly small. It's less than 0.05, and we were instructed that our alpha is 0.05. So that is less than 0.05. So the result then is to reject. Okay, so the p-value is less than the level of significance. Okay, so therefore we reject. Okay, so if the p is low, the null's got to go. So that means there is sufficient evidence to conclude that there is a linear relationship. Okay. Okay, so interpret the meaning of the p-value. So remember that the p-value is the probability of getting a value this extreme or more extreme given that the null hypothesis is true. Okay, so let's see which of these is the closest to that. So the p-value is the probability of getting an overall test statistic equal to or less than the sample result, assuming there's no linear relationship. Okay, so this is equal or less than. Okay, so that doesn't sound right. The p-value is the probability that there's a linear relationship between the dependent variable and at least one of the independent variables. Okay, that's not right either. The p-value is the probability of getting an overall test statistic equal to or greater than the sample result. Okay, so remember, the larger that f is, the less likely our null hypothesis is true. Okay, assuming there's no linear relationship. Okay, so remember that this is the null hypothesis, right? That there's no linear relationship, which would be the case if all of those coefficients are 0. Okay, so I don't need to read anymore. I know that that's the right answer. Okay. Okay, so now we have to compute the r squared. Okay, so I also on this, remember that the r squared is the amount of the variance in the dependent variable that we are explaining. Okay, so here's the formula for it. We're just going to take that regression, that sum of squares of the regression, and divide it by the sum of squares total. Okay, so what we have here is the sum of squares of regression, the sum of squared errors. The total sum of squares is going to be the sum of those, right? So I just need to add those up. Okay, so that's my SST. So I just need to take the ratio of this to get the r squared. Okay, so it's going to be equal to, so sum of the squares regression divided by total sum of squares. Okay, and so we need to round this to a 4 decimal places, so 0.2472. 0.2472. Hopefully I did that right. Okay. Okay, so now, the meaning of this r squared, this is set up so that this percentage here keeps the same number of decimal places here. So this indicates that 24.72%, right, of the variation in the appraised value, which is our dependent variable, can be explained by the variation in both of our variables, right? So land area and age, okay? Okay, so now the last part asks you to compute the adjusted r squared. Okay, so I mentioned at one point that we wouldn't need to do this, but this part of this question asks you to do this. It's not difficult. So we just need to make sure that we have all the pieces that we need. So just to go back to the slide I showed you during the lecture. So this is the adjusted r squared. The pieces that we need the r squared. So we've got this right here. Okay, and we need to know n. Okay, which we saw before. That was given in the stem of the question, right? So it's 32 homes. So n was 32. And then we needed to know k, which was just the number of independent variables. Okay, so we just need to plug all these things into this equation to get the adjusted r squared. Okay, so I'm going to go ahead and do that. Let's see. So it's going to be 1 minus, okay, then 1 minus, and our r squared was here, so I'll just put that there. And then, so it's going to be n minus 1, so it was, 32 minus 1, okay, divided by n, which is 32, minus k, which is 2, minus 1, okay, and close all the parens. Okay, so our adjusted r squared is 0.1953. Okay, let's see if that was calculated correctly. So 0.1953. Okay. Okay, and so as I said, number 6 and number 7, let's just skip those. But so I'm going to post this table, and hopefully, by making reference to this table, it will make question number 5 and actually question number 4 a little bit easier. Okay.